Hello and welcome to another episode of the Polymath World. We are so lucky today to be digging into astronomy and astrophysics a little bit more. I've got a wonderful guest here with me who has the coolest job title I've ever come across. She is a galactic archaeologist, and we're going to find out all about what that is and what that involves. Anke Arentsen-Ardern, thank you so much for joining me today. It's a pleasure to be with you.
Thanks for having me.
So I suppose the standard idea at the start for people who get into astronomy is that when they were little, they were just looking at the stars every night, maybe built their own telescope in their backyard. Is that what happened to you?
I didn't build my own telescope, but I did get interested from quite a young age in the stars and the planets in the solar system. I think that's where it started for me, with someone pointing out in the sky where the planets were, which were different from the stars. And I slowly developed an interest in it. And there was a local kind of observatory that my dad would take me to sometimes. And I really enjoyed it. So it started quite young. But then in school, I enjoyed physics and I enjoyed maths as well. So it kind of worked out in the end.
Are there any key moments in your childhood or when you were in school that you look at that really set you on a course to pursue professional astronomy?
I think it was just lots of little things, not one big thing. I think just being encouraged as well by my parents and siblings and teachers in school that this was an interest that is worth exploring.
Excellent. Did you ever want to be an astronaut, or was it always sort of looking at no, not at all?
No, never. For me, being an astronaut is too dangerous. I'd rather stay on Earth.
Yeah, it's quite safe to sort of sit on the ground and look up instead. So what was your route? University, master's, PhD, how did it all shake out for you?
So I studied physics and astronomy at the University of Groningen in the Netherlands. And I started it because I just really enjoyed it and I felt really at home. I'd also looked at some other study directions and really interested in languages, but I just felt more at home among science students. So I studied that and then I did a master's for 2 years afterwards. The master's was a year of courses and a year of research, and I really enjoyed the year of research. So that encouraged me to pursue a PhD afterwards. Just the ability to work with new data, to discover new things in an area that really interested me was my motivation for then going on to do a PhD. And so I did my PhD in Potsdam in Germany at the Leibniz Institute for Astrophysics.
Wow.
And there is where I really got into galactic archaeology.
Okay, so I'd love to ask you about what your research was on, but we've got to define our terms here. What is a galactic archaeologist?
Well, I guess thinking of what is an archaeologist, we're using very old things that we find in the ground to reconstruct a picture of what especially human history was like. So what we do in galactic archaeology is we use things we can find in the galaxy, in the Milky Way galaxy, to study its past, to study its history. So the correct term would probably be galactic paleontology, to use natural things to study the history of the world, but it doesn't roll off the tongue as nicely as galactic archaeology. So that's the term that's stuck and that now everyone in the field is using.
Excellent.
So specifically with very old stars is what I'm using.
Right. And in terms of getting into that, what was your master's and PhD research looking at?
So in my master's research, I studied the spectra of stars. So a spectrum of a star is where we split the light of a star in its different colors, and then we can actually figure out what a star is made of. So there's specific features that we can measure, and they're also sensitive to, for example, the temperature and the size of stars. So in my master's, I used the spectra to determine the overall composition, the temperature, and the sizes of stars. And in the end, it was a very, very useful experience that allowed me to get going very quickly in my PhD project. And in my PhD project, I was looking specifically at old stars. So these stars are billions of years old, 10 12 billion years old and have been around in the universe all this time. So they can really tell us about what the early universe, what the early Milky Way was like.
Mm.
Yeah.
Yeah, and spectroscopy is obviously a really invaluable tool for astronomy for all sorts of things. I mean, we use it a little bit in biology too for different things, but that's so I'm somewhat familiar. But I think children at school, they do learn quite early on about different stars in their lifespan. You know, the little blue ones, bigger white ones, big orange one, big red one, and then it blows up, that sort of thing. So, um, in that sense, what are the oldest stars in the Milky Way telling you?
So there's two types of old stars if you think about it in the context of stellar evolution. So an old star can be a star at the end of its life. Then for that star, it is very old. So that would be it's in the last phases. It's no longer on its what we call the main sequence, where it spends most of its life, but it's coming to the end. So for that star, the end of their life has come. But what I'm interested in is in the picture of the whole galaxy, a star that is old. So not just at the end of its life, but has been around since the beginning of the Milky Way. And the difference here is that stars of different masses live for different periods of time. So big stars live very short lives, they explode very quickly, and small stars can live for a very long time. So I study small stars that have been around for a very long time.
Wow. Are you looking at the death of stars as well? I mean, do you look at a lot of supernova?
I don't, because the stars that I study, they are, well, they're easier to study when they're still alive, because we can really study their spectra in a lot of detail. We learn different things from the supernova, but the supernova are very rare, and they actually only happen for massive stars, so they don't happen for the kind of stars that I study. So supernova is only stars that are more massive than about 8 times the mass of the sun. So the sun will never explode. It will expand and then slowly lose its outer layers and become a white dwarf at the end, but it will never actually explode. And the stars I look at, they're even less massive than the sun.
Wow. So, what is it about certain stars that enables them to live much, much longer despite being relatively small to others?
It's especially because they're small. So big stars, they're very hot as well, and they go through their nuclear fuel in the center. They go through it very quickly. So they just burn very quickly. They're very bright. They shine out all of their energy. And
Wow.
after 10, 100 million years, they've used up everything. They can't use it anymore. And then they implode and then explode. But a small star can actually just continue to fuse hydrogen into helium in its core for much, much longer, because it's more efficient in some way. Like, it just takes it a bit slower.
Wow, fantastic. It's really, really interesting. I first met you after you've got your PhD here in the UK. So tell us about how you came to the UK and in particular working at the Institute of Astronomy in Cambridge.
Yeah, after my PhD, I went to France for 2 years for my first research position, my first postdoc. That was for 2 years. So I worked at the observatory in Strasbourg and researched similar things as in my PhD. I continued some projects. I started some new projects with collaborators there, working on very thin streams of stars, so stars that are moving together kind of across the sky, that we think we're born together. And then I moved to Cambridge in the UK for my second postdoc, which is an independent fellowship. So it's 3 years of an opportunity to develop my research ideas and kind of prepare for the next step. And I've continued to work in the same field. Now that I'm an expert in it, I want to become even more of an expert in it. And so during my PhD, I started a project which is called the Pristine Inner Galaxy Survey, or PIGS for short. And in this project, I was looking for these very old stars in the center of the Milky Way, the very, very heart, which we think is the very oldest part of our galaxy. So this was a very big observational project, and I just had so much data that I kept working on it, kept developing the project, while also starting new things on the side. So that's what I've been doing in Cambridge, to continue with the PIGS project, but also dig into very new, very big data sets and see what we can find. So I'm really a data-based astronomer.
Yeah, that's fantastic. I'd like to dig into some of the tools of your trade here, because this can really interest younger students. What telescopes have you been able to use, and what kind of places in the world have you been able to go? Have you been able to use any of the most famous ones? And what does that look like in terms of practical research in your, month-to-month life?
So unfortunately, in my month-to-month life, I don't use telescopes very much. So the idea is, an astronomer, you stare up at the sky, you get your observations, and that's most of what we do. But it's not. I'm fortunate enough to actually have spent quite a bit of time at a couple of telescopes, because we had a project in the collaboration that I was a part of, and we got a lot of time on a smaller telescope, which meant that we always had to send people to go and do the observations. So this is the Isaac Newton telescope on La Palma in the Canary Islands, which is one of the old generation of telescopes where you really have to do everything. So you go, you get an introduction on the first evening with someone who's experienced, and then they leave you to it for the next few nights. And you open the dome, you set up the telescope, you make sure it's pointing in the right direction, and you spend the whole night observing. You make sure you use as much of the time that you have as possible, because you may only have 1, 2, 3, 4 nights, and want to get as many observations as you can as possible. So that has been really fun, and I learned a lot from that. So we don't look through the telescope. We sit in a room next door where we have a bunch of different computers and computer screens to be able to tell the telescope where to go, what to see, and we can keep track of what's happening, check if all the instruments are okay, check if the weather is okay, that it's not going to rain in the next 10 minutes. So you have to keep an eye out on all of these different things, because you don't want to ruin the telescope, obviously.
Yes.
And then I've been able to go to the Anglo-Australian telescope in Australia as well.
Right.
Which was actually the first time I went to the southern hemisphere. And I remember looking at the night sky during one of the observations. It's going out of the telescope, looking up and just seeing the Milky Way overhead, bright. And it was so beautiful. And yeah, that was one of the very special moments of my PhD. That was during my PhD. Because I could see what I was studying. I studied the center of the Milky Way, and I could see it right overhead, the big, bright center of the galaxy. But now, actually, most observations that I do are either remote, so I don't have to go there, or they do it for me. So I send them instructions, and they observe. So I've used a few other telescopes that way.
Oh, that's wonderful. Yeah, those moments are just wonderful. Would you love to go to Chile or have access to Hubble for a day or so? Is that an ambition of yours?
Yeah, I focus mostly on ground-based observations, because if you take these detailed spectra of faint stars, you need to have very big instruments, which are difficult to shoot into space. So that's why we have ground-based telescopes, because you can make them much, much bigger. You can build much more complex instrumentation. So like the cameras and the tools to split the light, they can be much more advanced if you're ground-based. But I'd love to go to Chile. I have used the telescopes, but only remotely by giving them instructions. So I currently have a program on the Very Large Telescope.
Excellent. Let's dig into Cambridge a little bit more. I believe are you a research fellow with Fitzwilliam College? Is that, have I got that correct? Brilliant.
Yes, so I have a position at the university and then also an affiliation at the college. That's right.
Terrific. Now, there's tons of history there. I mean, I've been lucky myself to go to the Institute of Astronomy many times. It's very, very famous in the history of astronomy, and you're constantly around some, not only a lot of history, but some really incredible people. What's it like for students who are interested in this field? What's it like working in collaboration at a place like the Institute of Astronomy in Cambridge?
I've really enjoyed it, and I've been reflecting on it recently. Why? Because I'm coming towards the end of my current position. And I think one thing is the people, but not necessarily the famous people, but it's my colleagues, my postdoc friends who are in the same field, who are in different fields. We really be able to support each other, not always talking about science, everything that comes with doing science as a job. How do you do this? How do you do that? What's your experience? And similarly, there is a community of students that is there. So in Cambridge, if you want to do astronomy, the first 2 years are natural sciences, so they're quite broad. And then in the third year, you can start to do astronomy specifically. And then you can do a fourth year that is again fully astronomy. And in those years, you really start developing a community of students that are doing astronomy together. I think it's really something that binds people. And it's a relatively small cohort, so it's easy to get to know people. And that's something I also really appreciated during my studies in the Netherlands. We were a very small group of students, but you really kind of grow up together as academics, which is really nice.
Excellent. Yeah, it's terrific. It's not as lonely as people might think of just the astronomer on their own looking through a telescope.
Not at all.
Not at all. Not anymore. So let's talk about the current state of your field. Firstly, what can you mentioned looking at stars that were sort of right in the heart or the center of the Milky Way. Now, general public understanding is that there's a massive black hole in the middle of the Milky Way. So is there a difference in the observations you would make there because of their proximity to the black hole, as opposed to if you're looking at stars on the edge?
The black hole doesn't affect my observations at all. So the black hole, in fact, only affects stars really, really close to it. So maybe, I don't know how to compare it, but maybe on a scale of 0.001% of the entire Milky Way. So it's like a very, very small part. So most of what I'm studying, it's not in the very, very center. It's not the inner 0.001%. It's the inner 10% of the Milky Way or something like that. So that's what we would call the center, the heart of the Milky Way. And this is a relatively large population. There's a lot of stars there. It's a very high overdensity of stars. And there's a lot of different kinds of stars or kind of groups of stars that are overlapping. So the Milky Way has a thin disk. If you see pictures of other galaxies, you see these beautiful spiral arms. The Milky Way has those spiral arms, but we don't see them because we're inside of the Milky Way. But if you could see it from the outside, if you could see it from above, you would see a flat disk with spiral arms. But if you see it from the side, it's just a very thin disk of stars. So this is where the most young stars are in the Milky Way. So this is where new stars are forming. Then there's also a slightly thicker disk that is a bit older. So you have a thin one, you have a thick one. They're still very, very flat. And then there's also a spheroid of stars, which is the very oldest population in the Milky Way. And they're all overlapping in the center. So this is a very complicated region. And then we're also discussing whether there's like a unique, different kind of group of stars there. And all of this is then connected to how the Milky Way formed, what was its early history like. And we know that galaxies grow from the inside out. So they start kind of small. In the early universe, you have a small galaxy. And then they start growing either by mergers, so they merge different galaxies together, and then they grow like that. And at some point, they've got so much gas that they can form a lot of their own stars, and then it's just building up its own stellar populations. And I'm interested in this very early phase. So this likely was a very chaotic phase of things merging, coming together, and those leftovers are left in the center because then the younger things start kind of growing on the outside. Right. So the spheroid is highest density in the center, and then it goes kind of out in all directions. So it's all in all directions, but it's only about 1% of all of the stars in the Milky Way.
Wow. So you think we can now pretty accurately put together almost a storyboard of the life of what happened to the Milky Way based on this data?
Yes, exactly. So a large revolution has happened in the past 7 years or so, thanks to the Gaia space mission. So the Gaia space mission might not be a mission you've heard about. You might have heard of Hubble or the James Webb Space Telescope. But Gaia has been absolutely revolutionary for every part of astronomy. It's not as exciting because it doesn't take beautiful pictures, but it measures the positions of stars and their motions. So that doesn't sound very interesting, but it gives us so much information. The positions are necessary to really understand what phases of life stars are in. So it teaches us about stars and how their life phases happen. But also you need to know their distance to know the 3D structure of the Milky Way. And then if you also have their motions, you can get a 6-dimensional picture. You can get 3 dimensions in space and 3 dimensions in velocities, because you can see then exactly where a star is, how it is moving. And if you make some assumptions about the distribution of matter in the Milky Way, you can use models to kind of calculate forward or backwards in time where a star would have been. So that means you can calculate the orbits of stars, like how they move in the Milky Way. Are they, going around in a circle? Are they going on ellipses? Are they going randomly? And this really gives us a picture of the Milky Way. So the disk stars, they move very differently from the spheroid stars. And then also, Gaia has a way to measure the composition of stars. So then you get another dimension or many different dimensions. And then we can really use that to piece together a detailed history of the galaxy.
And this was 7 years ago, this mission?
So Gaia launched, I think about 10 years ago. And then it took a while to collect its first data. And the first data release was kind of a teaser. And then the second data release was in 2018. And then it started changing the whole field of galactic studies, stellar studies. It also produces a very precise reference frame for like the coordinates on the sky. And it has observed everything, which is a completely new thing compared to other surveys, which usually you have to say, I want this star, that galaxy. But Gaia just observed everything that was brighter than a certain brightness. So we get a very complete map, very homogeneous. It's all observed in the same way. Again, previously you had, one telescope observed a bit of that, one a bit of that. So now for the first time we have this beautiful picture of all of these different properties of stars in the galaxy and how things are moving.
Wow, what a fantastic picture. Yeah, and what a difference that must make for you. We were talking to Lord Martin Rees recently and about is astronomy in sort of quite a revolutionary period. We think about 10 years ago, the first gravitational waves. You've had the first picture of a black hole. And there's a lot of stuff that's happened in the last 10 years, which seems to be quite revolutionary. But now you have new tools as well, like the James Webb Telescope. He was talking about the extremely large telescope being constructed in Chile and what that could do. What are the big questions left for you in your field, and how excited are you about the near future of astronomy?
I'm very excited. I think it's a very good time to be an astronomer. And we're getting into a phase where we're really getting into big data astronomy. We have so much data that we really need to update our methods to be able to still learn from it. But then there's so much that we weren't necessarily looking for in the first place that we can discover in these big data sets, which is really amazing. So usually when you design a new project, you have certain questions in mind, you develop a science case, you write it up. And then when the project actually starts, there's completely different things that you're also starting to discover, which is amazing. So the science that we don't know is often very interesting, like the things we haven't thought of yet, but the next generation of astronomers maybe will think of looking for it. So I think that's one thing that's very exciting. Within the history of the Milky Way, I think this very early phase is still not well known exactly what happened. We're still looking for signs of the very first stars that are no longer around. So we found some of these, but we're getting into large enough data sets that we can actually pin down what their properties were. And then we can do the same thing by looking directly at the distant past with the James Webb Space Telescope. So they're also trying to find out what were the properties of the first stars, the properties of early galaxies. So we're trying to connect these things, the local observations of the Milky Way, where we have old stars. And then if we look at the distant universe, we're looking back in time, and we're looking directly at young galaxies that have just started to form. So these are two complementary ways of studying what happened in the early universe. And I feel like the James Webb Space Telescope has been going for a while, but it's only just really starting to get going. And people understanding what they're seeing, it takes a while once you've got the observations. you know there's something interesting happening, but exactly what this is. So I think these two will talk to each other more in the future. And then there's big questions around what is dark matter, what is dark energy. Dark energy is not something I think about very much, but dark matter really shapes the history of galaxies. And we don't know what it is. So this is an open question that no one knows how long it's going to take to answer. We keep hoping it's soon, but we keep not finding any evidence of exactly what it might be.
Wow. Are there any instruments that the public's not maybe so familiar with that are coming up that might answer some questions or give some interesting data?
I think there's some projects on dark energy that people are trying to measure more precisely the expansion rate of the universe, the way it expanded, sometimes with using spectroscopic observations, because you need to know what distance these are away, how fast they're moving. That's quite exciting. I think in terms of dark matter, there's different things you can do. You can study other galaxies and how stars move there, or how gas moves. Around the Milky Way, one type of object that is really sensitive is dwarf galaxies. So these are very small galaxies, maybe 100 times smaller than the Milky Way, or even less. And they're actually dominated by dark matter. So the motions of stars are mostly because of the dark matter and how much of it there is, exactly how it is distributed. So observations of dwarf galaxies are very important. Inside the Milky Way, there's also, I mentioned briefly before, these stellar streams. So these are very thin streams of stars of an object that is being destroyed by the Milky Way. So this used to be a cluster of stars or a dwarf galaxy. But if it comes into the gravitational influence of the Milky Way is actually ripping it apart. So you can get these very thin streams that are kind of moving along with the orbit of the object. And they're very sensitive tracers to the amount of matter that's inside of their orbit. So if they're at 100 light years away, they can very sensitively probe all the matter within 100 light years, or 100,000 or something. So these stellar streams are interesting for the perspective of studying what they are. Were they clusters? Were they galaxies? What does that tell us about the history of the Milky Way? But they're also very sensitive probes to dark matter. And especially if there's gaps in them or things that don't quite look normal, you can infer maybe they collided with a dark matter blob. So this is what people are thinking about to try locally to constrain the properties of dark matter, for example.
Wow. And I'm really excited for this extremely large telescope to be built, because that sounds really, really quite dynamic too. Hopefully we don't have to wait too long for that. I wanted to ask you here, I think you mentioned 12 billion years as like the oldest star that you observe. That strikes me as being so close to, I mean, that's so ancient. If the universe is sort of 14 billion years old, what does seeing stars that old tell you about the beginning?
Well, the oldest stars we observe are even older than 12 billion years. That was just a reference I gave.
Wow.
So the universe, we think it's about 13.8 billion years old.
Yes.
But after a few 100 million years after the Big Bang, you get the very first stars forming. So that quickly after the Big Bang, you have the first stars. We think the very first stars were likely very big, and that means that they would have exploded very quickly. So they won't survive until the present day. But they would have produced the first heavier elements, the first elements heavier than helium. And as soon as you have some of those elements, you can start forming very small stars. So immediately after that first generation of stars, you form stars that are small enough to survive until the present day. So these might be 13.5 billion years old. They would have formed really early on, just enriched by the very first generation of stars. Because nothing happens to them. Once they're born, they're there, and they just keep surviving. And some of those are in the Milky Way. Every galaxy will have its own generation of really old stars that formed early on. And then since then, we've continuously kept forming stars. So you have stars of all the different ages in the Milky Way. And then we can use the Milky Way kind of as a time machine to really go back to each of these different epochs.
Oh, that's terrific. That's amazing. And yeah, I did my first PhD on Sir Arthur Eddington, and it is who was at the Institute of Astronomy in Cambridge a century ago, and it's incredible reading about the beginning of the discipline of theoretical astrophysics and those sorts of things, and how, at the end of the 19th century, you still had some people who thought that stars, because we didn't know where they got their energy from, were maybe had wood kind of burning in the middle of them, and we're just stuck there. It seems ludicrous now, but it was only a bit over a century ago that people didn't know so many basic questions about stars. And thinking about how much things are accelerating now, um, what's the biggest questions on your table? What are the big things you'd like to see an answer to?
I mean, in broader astronomy, I think it would be dark energy, dark matter, maybe finding planets similar to the Earth that could potentially host life, signs of life. This has been a big discussion recently. I don't think that the community is convinced yet that we have found these things or that it will be easy to detect them. But these are big questions. In my field, I would love to really discover what the early Milky Way was like, and maybe find some really old stars that we cannot explain. I think that is the most fun thing. If you find something that you cannot explain, and then you have some more years of work ahead of you to think about what it might mean. And I think expanding down to the outer edges of the Milky Way will be interesting as well. We'll get these maybe these streams that are very sensitive to dark matter. I don't work on the modeling side, but I think it always goes hand in hand. The observations, the models, the simulations. And as I mentioned before, the models there's really a need to have more complex models to explain all of the wealth of data and all of the details of the data that we have now. So I'm really excited to see developments there as well.
Mm. I just because I'm interested, I want to throw out a few more questions, if that's all right. The idea that the Milky Way galaxy is going to collide with another one in a couple of billion years, can you infer that happening with galaxies elsewhere, and what the effects of two galaxies bumping into each other does?
Yes, we see galaxies merging all the time in the universe. So if you look at, for example, the Hubble Space Telescope archive, and you look up pictures of galaxies, anything that doesn't look neat, like spiral or round, will be a merging galaxy, or a galaxy that has recently merged. So you have these beautiful, for example, the antenna galaxies. They're two kind of cores, and then they're kind of connected with a bridge, and you see a huge amount of new stars forming in these galaxies. So they're very bright patches of blue and red and things happening. So that it does happen all the time that galaxies merge, and we can infer that galaxies have merged with the Milky Way in the past. So we think about 8 to 10 billion years ago, there was a galaxy maybe 20% of the size of the Milky Way that merged with our galaxy, and we can still see the traces of it. So these stars have slightly different chemical compositions, which tells us they were formed somewhere else, and also different properties in the way they move. Like they have orbits that go very in and out of the center. They don't move very circular. So we can use that to infer that this galaxy merged with the Milky Way at about that time. Then about the future, there's been some suggestions that the Andromeda galaxy, which is our very big neighbor, so similar size to the Milky Way, will merge with the Milky Way in, don't remember exactly when, maybe 5, 6, 7 billion years or so. So if you know the precise motions of both galaxies, you can predict where they will be in the future. And it looks like they might be merging. But there's also been new observational evidence that maybe they're not directly on a crash course at the moment. So it might take a bit longer for that to happen. Eventually, it is likely to happen. We are in the same group of galaxies. We're bound together by gravity. And if you give it enough time, it will merge with each other. So what will happen? By that time, the sun will no longer be around. The sun will have become a giant and then a white dwarf. But mostly what happens is that the galaxies kind of move through each other. The galaxies are mostly empty space. The stars are very, very far away from each other, so it's mostly empty. So they move kind of through each other, but they feel each other's gravity, which is why they keep coming back together, and then they kind of merge and become one big new galaxy. So this would be, some people have called it milkdrometer, the mix of the two.
Wow. You did touch on briefly the future of our own star. Can you tell us, just to the general audience, like what the future of the sun will be, and what that process will look like?
So there's nothing to worry about. It's going to take a long time. So the sun has been around for about 4.5 billion years, and it has another about 4.5 billion years to go before it is at the end of its life. So stars like the sun, which are kind of small stars, they will, at the end of their life, they'll become giants. So they'll kind of swell up and become very, very big. And at some point, they lose their outer layers. So there'll be some winds that blow them apart. And then they get given back to the Milky Way, to the interstellar medium. And what's left is the core of the sun, which will then be exposed, and we'll call it a white dwarf. So white because it's going to be very, very hot, and hot things glow very, very white. And then it will slowly, very slowly cool and become less and less hot over time. But that will take a very, very long time.
Yeah, so don't worry, those of you who are at home listening. Thanks. This is really, really amazing. We love talking to astronomers here and astrophysicists. What's your advice to young people who might want to follow your career path? What should they do? What sort of steps should they take? What should they look out for? Could you just, give some advice to young students?
Yeah, astronomy is a science. So if you're interested in the sciences, that is a good direction. It requires a lot of physics and maths. So if you want to go into astronomy, do those courses, physics and maths. If you want to, you can try to start computer programming. There's a lot of computer programming that's used in astronomy, whether you're on the data side, modeling, or the simulation side. In university, you will learn maybe a little bit to program, but you'll have to use it if you do if you want to do any kind of research. And just look out for opportunities to engage with science. Look up things on YouTube. Try to stay excited about the topic, and then try it out.
Yeah, I noticed not all that many universities in the UK offer an undergraduate degree in astronomy. You kind of just have to do physics. Interestingly, there are a lot of mature college, like part-time programs for people to do astronomy. So those of you who are a bit older and want to get interested and study, there are routes for that. But is it just the case, you think, that the majority of students would have to study a maths or a physics degree and specialize later?
Yeah, most people would go through the physics route, and this is necessary because astronomy is one of the branches of physics. Like climate physics or nuclear physics, astronomy or astrophysics is one of those directions. And you need to have the basics first before you can go on and do astronomy. Because astronomy, you really need to know about physics, all the different aspects. It's gravity, how does gravity work? How does light work? What's the electromagnetic spectrum like? What are atoms made of? Nuclear fusion? All of these different things that you start learning in high school if you do physics, but then really go deep in the next level in university. And you need to understand them. You need to have the tools, which you can then apply to objects in space. That's really what astronomy is. We apply the laws of physics. We use mathematical tools to learn about the universe.
Amazing. And if people want to specialize particularly into your field, it's going to be master's and PhD, is it?
Yeah, depending on what you want to do. If you want to go into research as a career, you will have to do a PhD. And to do a PhD, you have to do a master's degree as well. But then not all people stay in astronomy. There's not enough jobs for all of us to become professors. So a lot of people do astronomy for a while because they enjoy it and they're curious and that's how they want to spend their time. But you learn so many skills that you can then apply in other areas like computer programming, like data science, like critical thinking, like problem solving. So even if you're not sure whether long term you want to go into research, it's still very much worth doing it and getting those skills in a way that you enjoy obtaining those skills, which is one of the ways that I think about it as well.
Terrific. If people want to find out more about you and your research and the things you're working on, where should they go?
You can Google my name and find my website.
Great, terrific, nice and easy. And the same with the Institute of Astronomy. I encourage people to check out the great work that's going on there. Brilliant. Thank you so much for joining me today, Anke. It's been really fantastic hearing from you. And I really hope if we do a astronomy roundtable or something like that in the future that we can hear from you again.
That'd be great. Yeah, thanks for having me.
Thanks for joining us. Thank you so much for watching. Don't forget to like and subscribe. Stay tuned for more amazing conversations with incredible researchers who are changing the world we live in and driving humanity forward. Feel free to check out my Instagram at polymath_Sam or go to my website at www.sam-mckee.co.uk.